All right, thank you very, very much. So first, I'd like to thank the organizers for inviting me once again to speak at this school and giving me this opportunity to tell you about some of the work that we've been doing to explore novel states of matter in twisted graphene. I'm sure by now you all know that one of the fun aspects of condensed matter physics is that it gives rise to a whole range of novel ground states. And on top of these ground states live very peculiar excitations. And if you ask, well, what is the kind of most important ingredient that is responsible for a lot of these phases, it's interactions. Interactions, as we'll see today, lead to correlated ground states. I'm sure you've heard a lot about that already in Philip's talks. Spontaneous symmetry breaking, which I'll talk more about today, as well as novel excitations. And you may ask, well, how can we enhance the role of interactions, since interactions is really what's responsible for much of what's going on? And one way is to consider flat bands. The band dispersion, of course, leads to kinetic energy of electrons, and having flat bands means that the kinetic energy is suppressed, making interactions a more dominant player in the physics that is taking place. Adding to that, also topology, which of course leads to interesting surface fault correspondence and non-trivial quantum geometry that I'll talk much more about today. Putting all these together gives rise to a very, very interesting set of phenomena that is governed by what I call a delicate competition between fractionalized electron liquids and symmetry broken charged solids. And I hope all of this will become much clearer as we go along today through this talk. And the focus today is twisted bilayer graphene, where a lot of this competition is taking place. And you'll see that very small changes in parameters like magnetic field or density could lead to very, very different underlying ground states that are competing for the lowest energy phase in the system. So the closest system that has flat bands, interactions, and topology is quantum Hall physics. And I'm sure all of you know quite a bit about quantum Hall physics, but I'll just kind of review it very, very briefly here. So imagine we have a two-dimensional electron system. Electrons are confined to the plane and subject to a very strong quantizing magnetic field. If one solves the single particle Schrödinger equation in this system, one knows that we end up with Landau levels. And they're shown here to be broadened because of disorder, which unfortunately we cannot escape. And one of the interesting aspects of the quantum Hall physics is that when we put the Fermi energy in between Landau levels, so in the gap, the system acquires quantized transverse conductivity, namely the voltage measured perpendicular to current flow is quantized in units of this universal constant E squared over H. And the constant here is something that I'll talk a lot about. It's called the churn number. Now, this is the integer quantum Hall effect, and it's basically can be understood in terms of single particle physics. But of course, if we fill a Landau level partially, in the single particle physics picture, we're not going to get quantized transverse conductance. So the transverse conductivity is not going to be an integer multiplying this universal constant. But if interactions are present, as I'm sure you've all heard, fractional quantum Hall physics emerges, which leads to a interaction-driven gap forming at some partial filling. For example, 1/3 filling of this second Landau level. And under these conditions, the system again acquires this universal transverse conductivity. Only this Chern number here, this factor C, is fractional. And one can show quite rigorously that if this Chern number is fractional, this is almost as being synonymous with having fractionalized excitations in the system, namely the elementary excitations in the system can be thought of electrons that are fractionalized, and if filling is 1/3, then this fraction of these fractionalized excitations consist of a charge E over 3. Now, already in the beginning, early days of quantum Hall physics, and in fact, what really motivated the initial search to go and would study two-dimensional systems at large magnetic fields was actually the search for a Wigner crystal. So people believe that if you take a 2D system subjected to a very strong magnetic field, the electrons, because of the Coulomb repulsion, would like to order in this kind of triangular lattice and form a Wigner crystal. And the surprise was that they discovered the integer quantum Hall effect, later the fractional quantum Hall effect, which basically is a liquid of some novel excitations. Here I'm plotting composite fermions that I'm not going to talk about, but basically they're not, this is not a solid, there's no spatial order here, there's no translational symmetry breaking, and yet this liquid phase of fractionalized excitations has a lower energy, slightly lower energy than the Wigner crystal. And only under certain conditions, for example, when the particles are holes and the filling is not 1/3, but maybe 1/5 or 1/7, does one enter a Wigner crystal. So already in the fractional quantum Hall case, people realize that there is a delicate competition between solids and liquids, and you'll see this today appear very, very prominently in the studies that we are performing on twisted graphene. So really, hopefully shed some light on what governs this competition between a fractionalized liquid and a charged solid. And as I mentioned, again, this is kind of the take-home message. There's really a delicate competition between fractionalized electron liquids and symmetry broken charged solids. Now, I wanted to give you a little bit of kind of my own interest. Why am I interested in this field? Well, I've been interested in fractional quantum Hall effects in physics for a very, very long time. It's 40 years since the discovery, and it's still a very vibrant field. Only recently, there's been some really beautiful experiments measuring anionic grading of fractionalized excitations. My own personal interest, together with Philip Kim, is to look at hybrid superconductivity and quantum Hall edge states. And the reason is that this hybrid physics can lead to new particles, which are known as parafermions. They have very interesting grading statistics, non-abelian statistics, and they can be realized if you're able successfully to integrate superconductivity with these chiral fractionalized edge states. So this is part of our motivation, but of course, in the real fractional quantum Hall regime, where both fractionalized excitations exist, superconductivity does not exist, and you need really large magnetic field and low temperature to have this phase, which is not the thing that superconductivity likes. So marrying these two phases, superconductivity and fractionalized quantum Hall physics, is very, very hard. What you'll see today is that twisted matter actually offers a platform for realizing fractionalized phases at zero magnetic field. So I'd like to start kind of a pedagogical section of this talk by providing a topological interpretation to the quantum Hall effect. And this is an interpretation that came about very early on after the discovery of the integer quantum Hall effect in 1982. Four authors, Dowless, Komoto, Nightingale, and Nice, realized that this universal transverse conductivity has a geometric interpretation. And the way they understood it is, first of all, by eliminating the boundaries. So we know if we have a topological system, there are chiral edge states, but what if the system doesn't have any edges? And the way they constructed it in 2D is to fold this 2D plane with its magnetic field acting perpendicular in a kind of a Gedanken experiment onto a torus. So basically they merge the left edge with the right edge and the top edge with the bottom edge. This gives you a torus. So now the system has no edges. And in addition to the magnetic field that is perpendicular to this torus at any given point, that's giving us the quantized Landau levels, they have introduced two knobs, which are basically gauge knobs, right? These are fluxes that penetrate the torus through its center, and another flux that penetrates the torus inside it. And let's label them phi x and phi y. These are gauge fields. In principle, we can gauge this away by modifying the wave function. And they considered the complete wave function of a full Landau level. So they filled up the Landau level, one Landau level completely. And they asked, well, how does this wave function of this full Landau level evolve as we change these tuning knobs, phi x and phi y? So obviously these wave functions depend on these parameters phi x and phi y, but they're periodic, 2 pi periodic, because once we add one flux quantum, we can gauge it away. So you can think of these functions as living on a Brillouin zone, where the periodicity here is phi x going from minus 2 pi to 2 pi, phi y going from minus 2 pi to 2 pi. Now, because these many body wave functions depend on these flux, one could invent a vector potential called A here, which describes how these wave functions evolve when we change this flux. And this is kind of an artificial construction, but it's shown here. It's basically the mean of this operator, v by d phi. And because it's a vector potential, it has two components. When the derivative is with respect to x and when the derivative is with respect to y. And if it's a two-dimensional vector potential, I could look at its curve. So f here is just the curve of this vector potential. So the derivative of ax with respect to phi y minus ay with respect to phi x. And what they were able to show mathematically and analytically is that if one integrates this function f, that's also called the Berry curvature, over the entire Brillouin zone, over all allowed values of these fluxes, one gets an integer, and this is precisely the integer that comes into this transverse conductivity. So the Hall effect, the quantized Hall effect, is simply a manifestation of the fact that when you integrate the Berry curvature across the band, for all values of these parameters phi, you end up with an integer, and that's what you're going to measure. Now, I want to emphasize that in the quantum Hall regime, it turns out that this function f, you see it's a function of flux, basically, of these parameters flux, but it turns out that it's essentially a constant. Because the bands are flat, and so as you're integrating over this flux, you're basically going to get a constant contribution, but in total, it gives you this integer value. So what's the relation between this geometric interpretation of the quantum Hall effect, which is the high magnetic field physics, to the one of today? So we are interested in lattice models, systems that basically, these are condensed matter systems that have periodic potentials in space, so they break translational symmetry, but continuous translational symmetry, but they have discrete translational symmetry. And we know that in these systems, we have block wave functions, and these block wave functions are described in terms of the momenta within the first Brillouin zone. And so we have these functions here, the block functions, as a function of momenta. There is no magnetic field here. This is just simple particle physics of the bands in the first Brillouin zone. Obviously, this function is also living on the torus, because once kx goes to 2 pi over the lattice vector, basically reaches the end of the Brillouin zone, it gets folded to the other side, and the same with dy, with ky. So this function, in effect, can be thought of as living on the torus very analogously to what we described before. And here again, we can describe a vector potential, describing how these block wave functions vary when we change momentum within the first Brillouin zone. And we can define a quantity that we're going to call, again, Berry curvature. And the peculiar thing here is that if the integral of this Berry curvature defined on this block wave functions over the entire Brillouin zone is non-zero, the system will have a transverse conductivity given by E squared over C. So this C number here is a Chern number. It's the integral of this Berry curvature over the first Brillouin zone, which is a local quantity, depends on momenta. So this function is a local function within the first Brillouin zone, and its integral is giving us the Chern values of these bands. Now, typically, if the system doesn't break time reversal symmetry, then obviously you're going to have at least two bands. If this Chern number is not zero, you're going to have, maybe it's going to be one, but then there must be also one that's a minus one, so that you're filling them simultaneously, and the total Chern number in the system is zero, because obviously you can see that if you have a transverse conductivity that's not zero, this means that time reversal symmetry has been broken. But this is for each one of the bands, but if time reversal symmetry is not broken, it means that we have two bands, so that the total Chern number in the system is is 0. So I hope this is clear, because this is going to be kind of a workhorse for us, this Berry curvature. And remember, it's a local quantity across the Brillouin zone. And how this Berry curvature distributes across the Brillouin zone is going to be a really important ingredient that tells us what underlying phase is going to emerge. Is it a fractional Chern insulating state, ones that carry fractionalized excitations, namely some kind of fractional electron liquid, or it's a bigger crystal where the underlying symmetry that's broken is translation. So what we understand today is that there are two ways of reaching or basically realize fractionalized excitations. One is the first one that I described, namely the fractional quantum Hall effect. Strong magnetic field acting on a two-dimensional system, quantizing the levels, so the magnetic field is first responsible in quenching kinetic energy, fighting flat bands. Second, interactions are important, and together these two give us a fractional quantum Hall effect. But now the question is, now that we know that we can have a lattice system that has Chern values, it will have transverse conductivity just like the integer quantum Hall effect. The C number is not 0, but in the absence of any magnetic field. And so we can ask, well, can we fill one of these Chern bands partially, and yet turning on interactions will give us fractional excitations? And this question was answered about a decade ago by a bunch of theorists. And the conclusion was that yes, in principle, one should be able to create fractional Chern insulators, so a system with fractional Chern numbers carrying fractional excitations in the absence of any magnetic field, where the starting point are these Chern bands, bands that have a finite Chern number, even though we don't have a magnetic field on. And of course, you will see that there are competing phases, which are Wigner crystalline phases that compete with these fractional Chern insulators. And so this is really kind of the topic of today's talk, is starting point, Chern insulating phases, and then with interactions giving us a variety of phases, competing order for the lowest energy states. And as I mentioned already, for us, this kind of direction in terms of long-term research is really exciting, because if we can realize fractional Chern states at low magnetic field, as you all know, in these twisted materials, there's also superconductivity at some different gate voltage. And so together, one could realize these parafermions potentially at very low magnetic field without having to struggle with hybridizing an external superconductor with these complex edges. All right, so now a little bit for the experimental portion. So the tool that we're going to be using is a kind of workhorse for us. It's a scanning single electron transistor, and I'll say more of what it measures. But it's basically a scan probe microscope. It has one needle, which has a sensitive device on it. I'll explain what this device is. And we approach this device very close to the surface. It's not touching the surface, and there's nothing flowing from the tip to the surface. So it's not invasive in any means. It basically is only electrostatically coupled. And with it, over the years, I'm just going to flash here and mention some of the things that we've been doing with it, because it's extremely versatile. So one thing we were able to do is to look at localized states of integer fractional quantum Hall systems and see that indeed the charge of the excitations is fractionalized. So as compared to filling factor 1, filling factor 1/3 shows 3 times more charging events when you're filling up the bands, indicating that the unit of charge is 1/3 that of filling factor 1, the integer 1. So really a direct measure of these fractionalized excitations. They're not only the figment of our imagination, they're really there. We were able to look at electron hole puddles in graphene, for example, the coexistence of what's called the Dirac fluid. Something that I maybe will mention just briefly is the ability with this tool to measure first order quantum phase transitions. And here we employed this capability to look at spin phase transitions in the fractional quantum Hall states. For example, filling factor 2/3 can have 2 underlying ground states, one which is a singlet and the other one which is a triplet. And you could really see very clearly the phase transition from singlet to triplet using this tool. Over the past year or two, we've been looking at how free spin waves or magnons in quantum Hall system bind to free electrons to form skyrmions. So this is an out of equilibrium phenomena, but basically the system finds a way again to lower its energy by creating these peculiar excitations known as skyrmions. And today's talk would be measuring the Chern number. So that's really kind of the thing that really captures a lot of these spaces was this Chern number that I described, which is the integral of the Berry curvature. And you might ask, well, the Chern number is an integral over all K space, all momentum space within the first Brillouin zone. How is it that the local probe can sense that Chern number? It's a topological invariant. Well, the fact is that it can, and it does it with very high precision, and there's very little uncertainty in our ability to determine what this Chern number is. And the advantage of doing it locally is that, as you'll see, when you study something locally, you can find a very pristine section of the sample that's not necessarily connected electrically to electrodes, which means the transport will miss it. But locally, we can see it very, very clearly. So first, a few words about this tip. So the idea behind this tip is that we have a small metal particle. This, in our case, it's made of aluminum, and two electrodes, two leads that are tunnel coupled to this small particle. And you can see how it's constructed. On the tip here, we have this metal particle, and on the side, we have the electrodes, and they're just tunnel coupling into this little metal island. And the reason we want tunnel coupling is we want the number of electrons on this island to be integer. If it was strongly coupled to the leads, then the electronic wave functions living on this quantum dot here would leak into the electrodes, and the charge is not quantized. So we need this to be tunnel coupling. What determines whether it's tunneling or not is the resistance across this tunnel junction needs to be larger than the quantum of resistance, 25 kilohms. But once it's beyond that, then we know the charge is quantized. Now, this puts a constraint on the energetics of this quantum dot. So typically, if you think of this quantum dot as a plate of a capacitor, and you think of the sample, which is sitting here below, as the other plate of the sample, then we know that the energy in a capacitor goes as E squared over the capacitance, charge squared Q squared over 2C. But now we can't tune the charge continuously. It has to be discrete. So if I plot this free energy as a function of the charge or the number of electrons, I do get a parabola, but I need to observe this parabola only at integer values of the charge, either n electrons, n plus 1, n minus 1, etc. And of course, for any value of the gate voltage, there's going to be a minimum energy configuration of the system that's going to determine what is the charge. And for a particular gate voltage here, voltage between tip and sample, that minimum is going to correspond to n electrons. So the system is really happy with n electrons. But if it wants to change the number of electrons, it has to pay an energy penalty to go to n minus 1 or n plus 1. And that means that electrons, if they want to flow from one electrode to the other, namely, they need to charge the dot to go to n plus 1 and then remove an electron, go back to n. This process is going to be suppressed. So there's going to be no current flow when this is the voltage on the electrode. But if we tune this potential difference just by a little bit, so that if this was a classical system without quantization of charge, the total charge would want to be n plus a half. Then we end up with a very interesting situation where the energy of n and n plus 1 are the same. This is not a physical solution, n plus a half. So this means that here, an electron can easily hop on, go from n to n plus 1, go back to n without paying any energy cost, and this means that current will flow. So the response of this device, called a single electron transistor, to an external potential is shown here. It shows peaks and valleys, strong peaks and strong valleys, which basically counts how many electrons are on this island one at a time. And you can see that if we position ourselves somewhere along this slope here, then we can determine strong changes in current to the device for tiny, tiny changes in potential. And that's the key essence of this technique. And just in terms of numbers, it has a charge sensitivity of 10 to the minus 4 of 1 electron per root hertz. Per root hertz, meaning we're integrating for 1 second. And you can ask, well, why do we need sensitivity of 10 to the minus 4 of an electron? There aren't any particles that have a charge of 10 to the minus 4. The reason is that not all the electric field from whatever we're studying ends up on our tip. And so we're typically not integrating the entire electric flux emanating from the charges we're trying to image. We're usually imaging just a very tiny portion, so having good sensitivity is very advantageous. In terms of voltage sensitivity and what potential can we detect, it's about a microvolt with a spatial resolution of about 100 nanometers. This is how it looks in practice. These tips are all homemade. This is a glass, a quartz rod of 1 millimeter in diameter. We pull it in a fiber puller down to a dimension of something like 50 to 60 nanometers. And then we do a bunch of angle evaporations and oxidation to end up with this precisely device. 1 island, 2 electrodes. The island sits exactly at the apex. And then we flip this over and bring it close to a sample, which is what is called here at the gate. So in the context of Landau levels, what do we know? So we know that if we have Landau levels in the system, the spectrum, the density of states has peaks when we're in a Landau level and has gaps in between Landau levels. If we're changing the density in the system, the chemical potential where the Fermi energy lies in the system will move fast across the gap because there are no states, and will move very slowly through the bands. So if we can monitor the change in potential, which is the change in chemical potential with our tip, as we change the density, we see that we're going to get peaks when the system is gapped. So this is a very cool thing, right? We're basically very, very sensitive to gaps. Whenever there is a gap in the system, our signal, this change in the potential that we measure with respect to density, is going to be maximum. So we're going to be following these gaps in the spectrum that tell us where the gaps are. All right, so we know how to measure gaps. The question is, how do we measure Chern numbers? And so here's a surprising fact about Chern bands generally. This is true for quantum Hall bands, and it's true for these lattice models that produce Chern bands as well. As we know, when we have a finite Chern number, the transverse conductivity is finite. But the peculiar thing about bands that have a non-zero Chern number is that the number of states in these bands is not constant. Let's think of a Landau level. We know that when we increase magnetic field, the number of states in the Landau level, its degeneracy is increasing. So this is an exact manifestation of the fact that when you're increasing magnetic field, the number of states in the band changes. This is very peculiar. Normally, when we think of bands, we think of a system that has a constant number of states. Chern bands have non-conserving number of states, and as you're changing magnetic field, you need a larger density in order to fill it. So Spreda realized that if we position the Fermi energy within a gap, and we ask ourselves, what is the relationship between the magnetic field and density that is needed in order to maintain the Fermi energy in the gap? That ratio in units of flux quanta is the Chern number. So imagine I'm sitting in the gap between 2 Landau levels and I'm increasing the magnetic field. The number of states within the band changes, so the Fermi energy will change. If I fill up the density back up to get into the gap, that ratio is precisely the Chern number. And here you can see an example, a measurement, where bright signal means gap. As I described before, this is a local measurement with the scanning single electron transistor. And you can see that as we're changing the magnetic field, the vertical axis, we need to change the density axis so as to maintain the system in a gap. And if you look at the slope is precisely 4. So this particular example, which comes out of a bilayer graphene with spontaneous symmetry breaking that we studied in 2010, provides us with a direct measure of the Chern number of 4. And in fact, you see that this Chern number of 4 persists all the way down to 0 magnetic fields, suggesting that this system actually is a quantum anomalous Hall state that was speculated for bilayer graphene. But the point is that it's this spread up relation that allows us to measure the Chern number simply by following the slope of the incompressible phase in this magnetic field density system.
Amir?
Yeah.
Yes, what is the color here? What color shows this?
Right, so the color is the signal dUdN. So you remember what we are measuring is change in potential for small changes in density. So it's an AC experiment. We're modulating the density in the system with a backgate. And we're looking at how the potential that the SET sees is modulating at the same frequency. That gives us dU, the change in potential with respect to density, which is an inverse compressibility. And that's the color scale here.
Because if you look at this slope of C equal to 4, it seems that at the top, there are regions of the red shows up, right? Red color shows up.
Right, so the magnitude of the signal you see is growing as you increase the magnetic field. So how big is this change? So remember, when you're in a gap, so if you're in a gap, when you change the density just by a little bit, if there was no disorder, the Fermi energy will jump from this full band here to the empty band above. Like you just add one electron and the Fermi energy will immediately jump to the next one. So dUdN is very large. If there is disorder, it's of course going to be smoothed out. But how big is this jump, dUdN, depends on the magnitude of the gap. And that's going to increase when you increase magnetic field. So in fact, I'll show it a little bit later. You can integrate dUdN over the density to get the change, the jump in the chemical potential. So it's a quantitative measure of the energy gaps in the system. Okay? All right. So we're going to employ this technique to twisted graphene. Kind of an optical micrograph of the sample is shown here. We're going to be scanning in the middle of this blue region here, where, as you'll see, it's quite steep. All right, so let's start at zero magnetic field, and we're looking here at the bottom plot, where on the horizontal axis we have filling factor, and I'm sure from Philip's talk already you know that in twisted graphene the degeneracy is, from -4 to 4. So at 4 we filled out the flat bands, and -4 we emptied them, and then what we see are these kind of dramatic changes in this inverse compressibility dUdN as we're filling out the bands. And there's a profound difference between the electron side on the right and the hole side on the left. Just to highlight what this difference is, you see that on the electron side, we see peaks when we enter integer filling. So the bands are fourfold degenerate. I'll say more about that in just a bit. But it turns out that they want to be filled one at a time. And each time you fill an integer band, there's a gap, and you see that there's a peak in the inverse compressibility, which tells us that there is a gap. And if we integrate these peaks, we get how the chemical potential is changing with density. And you see here that it's going up in these kind of abrupt steps. And this tells us what the energy gaps are, and you can see we can extract them. They're all on the order of 10 millivolts. So it's these are fairly large gaps, all driven by interaction, because single particle physics would say, hey, let's fill this fourfold band continuously until we get to full filling. So the fact that the gaps are open are an interaction effect that I'll talk about a little bit later. On the whole side, we see something very different. At integer filling, we have minimas. And this turns out has to do with what's called the cascade picture, and I'm not going to talk about it today. It is also manifestation of interactions, but a different one. And I'm going to leave it at that. So we're not going to focus on the whole side, at least not at zero magnetic field. In the upper plot here, what I'm showing is the same line trace, only plotted as a color plot, but now over position. So we're varying our location just to show that here, we're scanning roughly 1.2 micrometers, and you can see that the sample is very homogeneous, both in terms of the twist angle, as well as any other quantity. Nothing is really changing with position. It's a very pristine location in the sample. The reason we know the twist angle is not changing is because if twist angle changes, the Moiré unit cell changes, which means that the density to reach full filling is changing, but you see that this is straight up. It's not changing. So we know that this is both kind of uniform in terms of twist angle as well as any other kind of parameter. So now we take this line trace here, and instead of varying position, we're going to vary magnetic field.
Can we ask another question?
Sure.
On these peaks, on this gap, also can be seen via transport measurement. Can you see them in the resistivity?
Yes. So people in resistivity, when the system is in a gap, and depending on whether this, the Chern number of all the filled states is 0 or 1, then yes, you will see like a quantum Hall effect. So people see these, and I'll show this in transport in just a bit. I have some slides from related papers. Yes, you can see this both in transport. You can see the fact that you have these energy gaps using a scanning tunneling microscope. So there are a variety of techniques that you can observe the presence of fixed, kind of when the system is in a gap. Because remember, when the system is in a gap, it has a finite Chern number C, and that leads to a transverse conductivity that you can measure. In fact, it also leads to vanishing longitudinal resistivity, just like the quantum Hall system. Only the origin is not necessarily the magnetic field. So yes, but it's again here the key is that we're doing it locally, and as you'll see, it gives us a tremendous richness, something that is not seen in transport. And this is actually this slide. So what you see here is inverse compressibility in UDN color map as a function of density and magnetic field. And just to orient everybody, so these ±4 features are when the flat bands are fully filled. So now we have a big gap to the next band, and as you can see, when all the flat bands are filled, the total Chern number in the system is 0, and that's why the slope here is 0. It's just going straight up. But look at all these other features that have slopes here. Each time you see a slope, it means this system has a finite Chern number. And if you just choose a magnetic field and vary density, you see that the system is kind of trying to decide which Chern number it wants to arrange it at the same magnetic field. Alternatively, if you're at a fixed density and you're changing magnetic field, you see that the system is changing from one ground state to another very dramatically. And so the question is, what governs all these transitions, and what determines all these phases, and can we understand all these Chern numbers? What are they? So first of all, to just characterize what we're seeing here in the richness, let's kind of, instead of looking at the raw experimental data, which is what's shown here, let's distill it and just focus on slopes and intercepts. So this is this data set, and we wrote kind of an automatic script that looks for peaks, and remember, peaks are gaps, so that's when the system is gaps, and we're just kind of extracting every feature here, even if it's relatively faint, but that has a peak, and we've color coded them, but I want to kind of point out a few things. So for example, here at the bottom, from 0 magnetic field onwards, we have 2 features that are going straight up. Straight up means total Chern number 0. But they're peculiar because they intersect the density axis not at an integer number of bands. This goes to 3.5, and this is 3 2/3. So somehow when we partially filled one of these Chern bands, there is a gap state that opens, and it's a Chern 0 state. These red ones have a slope which is fractional. Therefore, as I'll argue a little bit later, they're fractional Chern insulators. Look at this yellow one here. It has a slope of 1, which means it's a Chern band with an integer Chern value. So it's not fractionalized, but yet it emerges when the band filling is 2 2/3. And onwards and onwards. And you can see that there's tremendous zoo of things here, where slight changes in density or magnetic field, for example, here, We're changing the magnetic field just a little bit, and we're going from these blue phases to the red phases. What governs this transition? So there's a lot to explore here, and I'll try to make some sense of it. I also want to point your attention to these black features emerging from the charge neutrality filling 0. So here you see a lot of these bands, and it looks like a Landau fan. And indeed it is. So if I have a band, and what's a Landau band? It's basically saying that in a finite magnetic field, I have Landau levels. So now quantization due to the magnetic field. But you see that they're all converging towards 0, which means that when I turn off the magnetic field, the density in the system goes to 0. As opposed to this black feature here, where as I lower the magnetic field, it goes to a finite density. So this is a Chern band that has to do with the lattice. These are Chern bands that have to do with the magnetic field. So the color coding here, just to get everybody oriented, green are Chern 0 states, slope is 0, and their intercept is an integer. We call charge density wave system, and the reason is because it breaks translational symmetry. These bluish features, these are also Chern 0 states, so they have a vertical slope. There are no states born as we change magnetic field, but they intercept the density axis at a fractional value. Symmetry broken Chern insulators are related to the charge density wave ones. They require symmetry breaking. You'll see it in a bit. They have integer slopes and fractional intercept. And perhaps the most peculiar are these fractional Chern insulating states where they have a fractional slope and fractional intercept. It turns out you can't get a fractional slope unless you have fractional excitations. So this is kind of the key feature. All right, so where is all this physics coming from, and do we understand it all? So let's take one step at a time. So just to remind you, twisted system, we have two rotated Brillouin zone of graphene. This gives us the mini Brillouin zone, and we have 2 K values and 2 K prime values. So that's why we have altogether 4 Dirac crossings. And so we have 4 valence bands and 4 conduction bands. And this Dirac crossings are protected as long as time reversal symmetry and rotation symmetry by 180 degrees are preserved. If, however, we break one of these symmetries, like rotation symmetry by 180 degrees, this could be achieved by aligning this Moiré lattice to HPN. This breaks this 180 degree rotation symmetry. The Dirac points get gapped, and the underlying bands, one can show with single particle calculation, they acquire finite Chern values. So this is exactly this interesting situation where you integrate the Berry curvature for each one of these bands, and you get a non-zero value. And the non-zero value is either plus or minus 1. And if the symmetry is just C2 breaking, when we're at the charge neutrality point, you see that the total Chern number of the 4 filled bands is 0 because we have 2 plus 1 and 2 minus 1. But now we can ask, well, what happens if we try to increase the density so that the total filling is 1/4 of the total possible filling? So effectively equivalent to filling 1 band. Of course, if interactions were not important, the way we would fill 1/4 or 3/4 of this band is just to give all flavors equal contribution. So we fill each one of these bands to 3/4 of its value. So the total filling would be 3 out of the 4 possible filling of the band. But of course, we know that once interactions are present, this is not what the system favors. What the system favors is filling out 3 bands entirely and selecting spontaneously 1 band and leaving it empty. This also has a total filling of 3, but it does not treat all the flavors in the same way. And the flavors, of course, here are spin and value. So they're altogether 4 flavors that we need to consider. And you see that if this is the case, then the system now, the total filling here of 3 out of the 4 has a total Chern number of +1. 1 Chern band is empty. And if it's a Chern number of +1, it has transverse conductivity. It's like a quantum Hall system. And if you measure this transverse conductivity, Rxy, this is the transport experiment, you see that it's quantized at 1. And when you change magnetic field, this is all happening at 0 magnetic field, remember. When you change magnetic field, it can select a different Chern number, which is -1. So which one of these flavors gets filled, it depends slightly on magnetic field, but nonetheless, it breaks that symmetry spontaneously. So this system breaks time reversal symmetry spontaneously, as well as the C2 symmetry that initially provided us with the band gaps here. These are, by the way, experiments in transport started from Goldhaber-Gordon's group, and then Andrea saw this very clearly. Andrea. What happens when we consider time reversal symmetry breaking? Well, time reversal symmetry breaking, it turns out that the 4 bands that are filled at neutrality all have the same Chern number, and the ones that are empty have the opposite Chern number. So this means that when we're at charge neutrality, the Chern number is 4. This is very similar to the example that I showed you before when I introduced the Strela formula, where the Chern number is 4. And here, these are SDM experiments from the Yazdani group, and you can see that its filling factor, starting from the charge neutrality point, when you change magnetic field, there is a slope here which corresponds to the slope of 4, meaning that the states in these bands are increasing in number, and you have to follow a slope of 4 in order to keep the Fermi energy in the gap. But now let's ask, well, what happens when we go to filling factor 1? Well, if we go to filling factor 1, we now have a total Chern number of 3 because we've compensated one of the flavors. So now the slope is 3. And then for filling factor it's 2, it's 2, and for filling factor 3, it's 1. And this is what they see in experiments, suggesting that the underlying mechanism in this particular symmetry broken case is time reversal. So I want to point out a very important feature of all these measurements. And that is that if we add up 2 integers, the integer that corresponds to the band filling and the integer that corresponds to the slope, it always must be an even number. And why? When we change the filling factor, if we're filling one of these bands, when we change the filling factor by 1, we're also changing the Chern number by 1. And so the sum of filling factor and Chern values always must be an even number. Okay, so remember, always has to be an even number. And this is something that nearly all experiments in transport see consistently. So let's look at our data. So this is kind of a zoomed out picture, only highlighting some of the stronger Chern bands that we see in the experiments, but it's the same data set that I showed before with a different color scale, different just scale here. And again, here I've highlighted all the states that we see. And I've indicated in color whether the sum of the filling and the Chern number is even or odd. Even is what we understand. Up to now, all the picture that I presented is described in terms of even Chern number plus band filling. And these are the blue states. So you see here filling factor 3, a Chern of 1, that's okay. The sum is 4. A Chern of -1 plus 3, that's okay, that's 2. So all the blue ones are even, but you see that there are plenty red ones. Red means that the sum is odd. And this means that this picture of filling a fixed number of bands, each one of these bands leading to an integer filling, has an integer Chern value, and the sum is even, is not enough. Obviously, we're seeing very, very clear deviations of this. How can we understand what the odd fillings, the odd parity states are? They must have a different physical origin. So interestingly, again, the way to understand it is by considering interactions. But whereas up to now the ingredients were that we considered flat bands and interactions, and we wanted to fill up the bands entirely, in order to understand the odd parity states, we're going to have to restores some of the band dispersion. So we're going to have to argue that the bands are no longer flat. And in fact, this is something that there's growing evidence, both theoretically and experimentally, for. So whereas originally kind of the simple picture we considered single particle picture indicates relatively flat bands, it turns out that when you turn on interactions and you're moving away from the charge lethality, you're starting to fill up bands. You want to go to filling factor 1. So you're sprinkling charge in the system. That charge is not distributed uniformly across the plane. It favors sitting in various locations on the AA sites or the AB sites. And what this means is that this potential that these electrons that we've deposited are providing is not a uniform potential. It adds another periodic potential, if you like, and it modifies the dispersion. And so it turns out that due to interaction, the dispersion of the bands is not as flat as one would imagine. So this might seem that it goes against kind of the role of interaction, because suddenly kinetic energy is important again. And indeed it is. And so let's see what some of the consequences of that are. So suppose I want to fill one of these, I want to fill a density corresponding to one of these bands entirely. So I want to go to filling factor 1. When the bands were flat, obviously interaction is favoring just choosing one flavor and filling it entirely. But if the bands are not so flat, filling a band entirely costs a lot of kinetic energy. And it actually might benefit the system to choose 2 flavors and fill each one to a half value, because this lowers the kinetic energy. You're also paying a penalty on interaction, but if kinetic energy is large, then that might be beneficial. And if we're already going to have filling, well, now if we just distort the unit cell by a little bit, such that we double the unit cell, a gap opens precisely at half filling, which lowers the energy even further. So what these 2 left panels are showing is the interaction enhanced dispersion. And then if there is a distortion that doubles the unit cell, you see that now the momentum goes only to half the value. And we folded half of the band back onto itself to give us 2 bands in this larger unit cell. Okay? Now, as you already saw, bands have to have an integer churn value. We cannot play with that. That's a geometric topological constraint. So we started with a band that had a churn number of ±1. We split it into 2 bands. Well, we need to assign some churn values to these bands. And it turns out the way this happens is that the bottom band acquires all the churn number, and the top one, which is fairly flat, acquires a churn of 0. So the number of bands doubled, and we have now suddenly churn bands that have a 0 churn value. The fact that all the churn on the Berry curvature is constrained to the bottom band comes from the fact that if you remember, this Berry curvature is a local quantity of the Brillouin zone. And if you plot its value across the Brillouin zone, you see that it's very much concentrated in the middle. And that's why all the bottom band acquires the full churn value and the top one gets 0. So now we can see that we can explain some of these odd features because we have double the number of bands. Some of them have churn ±1, some of them have churn 0. So let's focus, for example, on filling 3. So you want to fill totally 3 bands. Churn 0. This is an odd parity state. And so the way we would do it is we take one flavor, fill it entirely. Take the next flavor, fill it entirely. And then, as I explained before, I'm going to take 2 flavors and fill them up to half the value. This accounts for all the churning. All the Berry curvature in the system is accounted and is filled up. So we have a total churn of 0. And the filling is only 1/3 because we left 2 half churn 0 bands empty. So we see that the role of interaction here was to generate a distortion. And because this is a distortion, you can think of it as a Wigner crystal. Obviously, we've broken spontaneously translational symmetry, and the system now has a churn 0, but an integer filling such that the sum, the parity here is not 0. We can do the same for any one of these red states, and I'm not going to go through the exercise. You can see the logic. It's fairly simple. So now we can move on to see some of these more interesting fractional intercepts. So these states that intercept the density axis at a finite value rather than integer, which means that we are filling the band only partially, and nonetheless a gap opens in the system because of interactions. So what is the nature of that system? So here I'm zooming onto this region here, a filling factor from 2.5 to 4. So it's this window right here that I'm going to be looking at. And on top is the raw data. And the bottom here is, again, the distillation of these churn, these slopes. And I want to point your attention to this yellow feature going all the way down to 0. It's a churn 1, so the slope is 1. But it intercepts the x-axis at 2 2/3, which means that when the band gets filled up to 2 2/3, only then a gap opens, and the system has now a total churn of 1. So somehow the Berry curvature adds up to give us +1. And here between filling factor 3 and 4, we have 2 churn 0 phases, one intercepting at 3.5 and one at 3 2/3. So what are these? So let's start with a half. So the one that has a 1/2 denominator here. So very similar to what I described before for the odd parity, we could use the same argumentation to create a half-filled churn 0 state. So remember, we have band folding, doubling of the unit cell, and the bottom band here has churn ±1, the top is a churn 0 state. And if we want to create a churn 0 and fill up 3.5 to 3.5, the way we would do it is to fill up 3 flavors entirely, and this time only one. The last flavor will fill up the bottom band, so the total churn number is 0, all the colors cancel, and we're left with half a band empty with a churn 0 state, which is precisely this one. So again, this is a fractional churn, and this is a bigger kind of a bigger crystal state at charge density weight, because unit cell has been broken and doubled, and but it's not a finite churn number. The slope is 0. Now, how would we describe the thirds here? So the denominator of 3. Well, here interactions need to split the bands into 3 bands. So we need to triple the unit cell. And again, when we triple the unit cell, all the Berry curvature gets assigned to the bottom band. So that one has a churn of ±1, and now we have 2 bands that are churn 0, each one containing 1/3 of the density of the total band. And so to get the churn 1 with filling 8/3, you can see that we take one flavor entirely, another flavor entirely. One flavor we fill up only 2/3 of the way, and we leave one empty. And this you can easily work out gives us a churn 1 and a filling of 8/3. So these are already quite peculiar states. And they're again manifestation of interaction, only here the role of interaction was to broaden the bands, in addition to all the others that want to fill up bands entirely. And similarly, this churn 0 11/3 could be seen and plotted here. So now you see that these churn states live from 0 magnetic field. So they're spontaneously broken even before we started applying a magnetic field. And now we're applying a magnetic field up to 3 Tesla, they survive. But now if we go to 4 and 5 Tesla, we see that they get replaced by these red lines. And these red lines are captured by a finite slope and a finite intercept. And a finite slope is a fractional Chern insulating state. So these must have fractional charges in them. And so the question is, how can we explain this, right? So remember, to get a fractional Chern state, we can't capture all the Berry curvature, because if we capture the entire Berry curvature of a band, it's going to be ±1. So we need something that captures only 1/3 of the Berry curvature in order to get a slope, which is 1/3. And the question is, so what's the competition, right? So this would be a picture that conceptually can describe a fractional Chern insulating state where we are opening a gap, but we are not folding the gaps because the bands, versus these charge density wave states that double the unit cell or triple the unit cell. So why would we favor one versus the other? And you can already see that the key ingredient is how the Berry curvature is distributed across the bands. And remember, Berry curvature is a local quantity. It's a local property of the Brillouin zone. It depends on momentum. So each state within the Brillouin zone has its own Berry curvature. And for the fractional Chern insulating states, we want a Berry curvature that's very uniform across the band. That's why when we fill a third of it, we can capture a third of it. Whereas for the charge density wave states, we want Berry curvature that's very localized to the band, such that when we fill a third of it, we already grab the full Berry curvature and get a full integer Chern value, 0, 1, 2, 3. So the measure that can capture how the Berry curvature is distributed across the band is known as the quantum, one of the metrics of the quantum geometry, and it's the variance of this Berry curvature. So instead of just adding it up to get the total Berry curvature of the band, we can look at the variance. This is going to tell us how it's distributed across the band. And what theory is arguing is that when this variance is below a certain number, the system would favor a fractional Chern insulating states, and when it's above a certain number, it would favor a charge density wave. So here is a plot of the variance of the Berry curvature calculated by exact diagonalization at zero magnetic field for this twisted material. And they're looking at this variance of the Berry curvature as a function of a parameter that's experimentally quite hard to control. And that parameter is just the tunneling rate between the A atoms, between the two layers, versus the tunneling between the AB atoms. And they're captured by the parameter W0 for the AA, W1 for AB, and here's the ratio. Experiments in graphene and kind of typical experiments, this ratio is on the order of 0.7. So it's sitting more or less right at the value here. But what their kind of first principle calculations show is that when the Berry curvature is above this 1.7 value, the system favors the ground state, which is the charge density wave state. And when it's below 1.7, it favors the fractional Chern insulating state. And the nice thing here is that they find a way of how to tune it experimentally, but this is practically very, very hard. So what are the knobs that we do have experimentally? So one knob is, of course, magnetic field, which, again, I don't want you to think of the role of magnetic field here as changing as quantizing the levels. Really, the role of magnetic field here is to thread a flux through the unit cell. And what they see is that when they're changing, oops, that's not the right plot, sorry. When they're changing the flux in the system, you can see that as a function of the same parameters, this variance of the Berry curvature favors more and more the fractional Chern insulating state. And the reason is that what the magnetic field is doing, it's basically distributing the Berry curvature more and more uniformly across the bands. And you see that you require only a very small fraction of 1 phi naught per unit cell, on the order of 0.1 phi naught, in order for the system, when it's characterized at this tunneling ratio 0.7, to undergo a transition from charge density wave to fractional Chern insulator. And in fact, for this parameter value of 0.7, which is, or 0.6, for which this is the experimental value, this flux value of 0.1 or 0.15 is precisely 5 Tesla in our experiment. So we believe that the reason that the system is undergoing from these blue states that are Chern zero states and charge density wave states transition to the fractional Chern insulator because we've supplied enough magnetic field and now distributed the Berry curvature across the band to favor this fractional Chern state. Now there's another experimental parameter that in principle one can tune. This is the twist angle. And you might argue, well, we should be at the magic angle. Well, it turns out that for fractional Chern insulating states, it's all these competing factors of how the barrier curvature is distributed across the band, what is the band width, which is a function of interactions, and all that needs to be optimized. And what theory is telling us today is that if we want to achieve fractional Chern insulator at zero magnetic field, we may want to move away from the magic angle, 1.0 something, 1.04 or 5 or 6. A little bit larger, this would favor a fractional Chern insulator already at zero magnetic field. And so we're conducting experiments to search for this. We certainly we haven't seen it at zero magnetic field. The lowest field that we see is precisely this condition here, where we need to turn on some flux in order to transition to the fractional Chern insulator state. As I explained, this is what flattens the quantum geometry of the system. Now, in the remaining just few minutes, and I want to leave some time for questions, I just want to give a few numbers about some of these peculiar states that we're posing. So first of all, as I showed in the beginning, we can integrate these gaps to give us these incompressibility features, to give us the energy gaps. And so here you can see that the energy gaps for these fractional Chern states is between 0.1 and 0.2 millivolts. So they're fairly fragile, and you need low temperature to see them, but nonetheless, they're clearly observable, and they don't seem to depend that strongly on magnetic field. This is actually, the energy scale here is consistent with some simulations using, that were done at MIT for these kind of phases. So this is encouraging. I also want to point out that we focused only on the two dominant fractional Chern insulating states, the 1/3 and 2/3 states. But in fact, there's a whole zoo of states that we're seeing, as you saw in the original picture here. These are just zoom ins of many, many states that we don't really understand. They have intercepts of a half and slopes which are peculiar. So there's a lot of things to be resolved here. And just to my main message for this talk, you see that all these phases live very, very close to one another. And so just some slight changes in density or magnetic field changes the underlying ground state of the system. So there's a lot of competing factors here, and we don't even know what are all the knobs that are important in deciding which phase wins over another phase. These are some more exotic charge density wave and symmetry broken state that we see. You see a lot of different vertical features and slanted features, the yellow and blue ones here, that I think require understanding exactly what the underlying border parameter of each one of these. And so there's plenty of work to be done here. Lastly, I want to point out something about the uniformity of these more fragile states. So what you can see here on top, these are the 1/3 and the 2/3 fractional Chern insulating state as a function of position, again, over a range of 1.5 microns. And you can see that this is the twist angle plotted on the left. And what I want to emphasize is that there are regions here where the twist angle is changing by very, very little, and yet the underlying ground state is changing. And this is something that we don't really understand, because it basically says that there are other knobs other than the twist angle that governs which phase dominates the system. And again here, this is something that requires more work. So with this, let me just acknowledge the people who've done the work. So this work was carried out primarily by Young Long, who came from Princeton, and Andrew Pierce, who's just graduating, and Someone Lee. Samples were prepared by the group Pablo Arilo Herrero, Johan, and Jane made these samples, and a lot of the theory insight comes from collaboration with Ashwin's group at Harvard as well. And so with this, let me pause and see if there are any further questions.
Thank you, Professor, for the wonderful talk with all the fascinating plots. And now we're taking questions from the in-person audiences first.
Yes, I have a question about this zero slope thing that we call them CW. Is it, so let's say if I give you a lambda Frank diagram of some unknown material, is it always true that when you see these zero perpendicular lines, always means that CW or means a strong correlation?
No, I don't think it has to be. So you can certainly, as you know, in graphene, for example, you can see a nu equals 0 phase, which has a total churn of 0. And then that has to do with spontaneous symmetry breaking that is not related to the charge to any translational symmetry breaking. When I say there is translational symmetry breaking, it's when the intercept is not integer. Because the way we can understand the intercept here, not just the slope being 0, but the intercept being a fraction, is that it requires a distortion in real space, which leads to folding of the bands in momentum space.
But
and this,
I think in nu equal to 3 also you had this perpendicular.
right, so nu equals 3 is, I would call it kind of a conventional churn 0 state. And it does not require, so remember, so at nu equals 3, churn 0 is an odd parity state.
Yes.
So because it's an odd parity state, it does require translational symmetry breaking in order to explain it, even though the intercept is 0. Is integer. So the odd parity states do require translational symmetry breaking.
And another question is that, is there any understanding why FCI and CW comes together?
I could not hear very well, so why?
Why FCI, the fractional Chern insulator, and CW come together for this?
Right, so you're asking why is this transition happening here?
And because for both of the feelings, after CW you have fractional Chern insulator. So my question is that
right, yes. So okay, so this is what I tried to explain. That is, when you start at 0 magnetic field, the distribution of the Berry curvature is such that it's very concentrated at the bottom of the gamma point. And this means that the way the system finds a way to minimize its energy is to create this distortion. For the half state here, 7.5, it doubles the unit cell. For the 11/3, it triples the unit cell. And you see that just going from here to here, I'm filling up the band. And the system decides to undergo a different, to realize different ground states. One has doubling of the unit cell, the other one has a tripling of the unit cell. These are not a family, right? You cannot think of this as something just being filled continuously. Something is really drastically changing here. And in fact, it's a first order phase transition that goes between this and that. And the first order phase transitions did not talk about it today, but they're captured by negative inverse compressibility. So you see this blue sign here goes to -1. So anytime you see a blue feature, it's very likely related to a first order phase transition. That's what's happening between these phases. Suddenly, there is a different ground state that's being favored over the first one. But as you're raising magnetic field, this kind of distortion and this kind of minimization of energy becomes less and less favorable because the Berry curvature gets spread more and more uniformly across the band. And apparently, at this 5 Tesla value, the system now has a Berry curvature which is uniform enough that the state that it wants to realize is a fractional Chern insulator state. I don't have much more to say beyond this very hand-wavy picture, unfortunately. Thank you.
So, hello, Professor.
Hi.
I want to make sure when you talk about the unit cell, it's a Moray unit cell, right?
I could not understand. Sorry.
When you talk about the unit cell, it should be
the unit cell, yes.
Yeah, it should be the unit cell after you twist your layer, it's a big unit cell, it's not the original small unit cell, right?
Right, so when I'm talking about doubling and tripling of the unit cell, you can think of forming stripes in the system, for example. That would, if you form some kind of charge density wave that creates a stripe whose dimension is twice the original unit cell of the Moiré lattice, then that would give you the kind of distortion that we need. But of course, we don't know exactly what the type of distortion that we have. I think it would be fantastic if one could see this distortion in STM. I mean, this is something that in principle should be visible in STM. The problem is that these samples are extremely high quality because they're encapsulated both sides. And as I mentioned, we're looking for a pristine section. For STM, you cannot have the top covered. So typically quality of samples is not as good. So it might take some time until these can be seen in STM experiments.
Thank you. Okay, so here we have two questions from webinar. The first question is, could you explain what differentiates a Wagner crystal from a charge density wave?
I don't think there's a distinction. I think I probably just use it kind of interchangeably. A bigger crystal is a charge density wave. It breaks kind of charge uniformity in a discrete fashion. So it's, yeah.
Okay. The second question is, during the charge density wave to fractional Chern insulator transition mediated by magnetic field, is the Barry curvature distributed over a larger part of the band or the band itself to get flattened?
Right. So the Barry curvature, when you integrate it over the entire band, has to add up to an integer. When you have a fractional Chern insulating state, you still need to integrate the Barry curvature to get an integer. The reason you get a fractional Chern number is because the excitations are fractionalized. So remember, the prefactor e squared over h, which is the unit that multiplies the Chern number, has the unit of charge in it. And if excitations are fractionalized, that's why you get kind of total transverse conductivity to be fractional. It turns out that the Barry curvature, when you're in a fractional Chern insulating state, is not uniform. In fact, there is a limit. There's a model that's called the chiral model that was introduced by Ashwin that takes the limit of these tunneling values, W0 to W1, to be 0. And in that limit, the bands can be calculated precisely. And one finds that these flat bands are precisely flat. They're kind of mathematically flat. But if you calculate the Barry curvature in these flat bands, it's not uniform. So these flat bands still have finite variance of the Barry curvature. Luckily, for the fractional Chern insulating states to exist, you don't need uniform distribution of the Barry curvature. It just needs to be flat enough. The quantum geometry has to be flat enough to favor that state over other states.
Okay, yeah, thank you again for the wonderful talk, Professor.